Hello friends, this is Jim with Science Talk. In this video, I want to discuss with you the issue of potable water. 2/3 of the world worries about water for at least a month annually. One successful source of salt-free drinkable water has some problems with it. So basically, salt-free drinkable water comes at a cost. What does that mean? You've probably heard of, we're basically talking desalination plants. Now, desalination requires a shitload of energy to engage in the process. Shitload of energy. And as the glaciers melt, the alpine glaciers melt, which and the snowpacks in the Sierra Nevadas or the Rockies here in North America. People, towns have relied on a slow melt that will supply them water for the rest of the year until the winter snows reappear. Well, now if those alpine snowpacks are disappearing, alpine glaciers disappearing, there's an issue of fresh water being available. Now, if you live near the ocean, well, you can take the salt water, remove the salt, and drink that. That's a very intensive process. Yes, it's gotten more efficient. It still uses a lot of energy. Now, you could go to the Arctica regions, the polar regions, and you can go to the sea ice, and again, it's called sea ice because it's the source. The ice is via the source is the sea, because as the sea ice forms, the salt is not contained in the ice crystals. It is what's called brine rejected. It's brine rejection. So basically, you can take that sea ice, you can melt it and drink it. It is potable. You might want to do a little filtering to get rid of any little organisms in there, that kind of stuff, but it's potable water. Well, of course, now what's happening, there's less and less sea ice, Arctic sea ice, right? Certainly a reduction in the multi-year sea ice. So, around the world, there are approximately 16,000 desal plants. They're now obviously purifying the seawater and brackish aquifers. Brackish, basically another word meaning containing salt. Seawater typically has salinity, depending what oceans you're in, of at least 30 parts per thousand. On average, like the Atlantic is about 34 parts, the Pacific about 33 parts. Brackish water would be something like for estuaries, where we see, depending on where the tides are, you can see the salinity anywhere from 10 to 25 parts per thousand. When the tides come in, the salt water comes in, that's when it would go up as it mixes with the fresh water that's already there. Now, these 16,000 desalination plants produce about 95 million cubic meters of fresh, salt-free drinkable water daily, which is about approximately half the daily flow over Niagara Falls. But there's a potentially polluting price to pay. For every liter of fresh water, the same desalination plants produce approximately 1.5 liters of basically toxic brine. That adds up to enough in the course of a year to cover the entire state of Florida to a depth of more than 30 centimeters. 30 centimeters is a foot. Imagine putting this amount of salt all over Florida. A new study urges nations to explore better solutions and new ways to exploit the minerals in the wastewater and support efforts to advance what the UN has declared Sustainable Development Goals of reliable, safe water on tap for everybody in the world. And of course, this study is looking at brine, but they don't discuss the energy run the plants to make the drinkable water. And that is another issue, as I've already mentioned. A second study confirmed that the Sustainable Development Goal of clean water and sanitation for everybody by 2030 is likely to cost around $1 trillion a year and up to 8% more if the advances are matched by efforts to contain climate change and limit global warming to the agreed level 2 degrees C above historic level by 2100. Well, that ain't going to happen, I'll be blunt. I don't think that is. We're at 1.3, we're going to blow past 1.5 soon. I don't see keeping it to below 2C by 2100. I really don't. 4 out of 10 of the world's people face severe water scarcity. It's 40%. More than 6 out of 10 experience at least 1 month a year in conditions of water scarcity. There are now desalination technologies that work in 177 countries, 2/3 of them in nations with high incomes. Well, okay, they can afford it. But what about the 1/3 that can't? Researchers from the UN University's Institute for Water, Environment, and Health, UNUINWEH, there is an acronym, and from the Netherlands and Korea report in the journal Science of the Total Environment that they found that 55% of all the hypersaline brine was produced by just 4 Middle Eastern nations. China, the US, and Spain produced the rest. Small island nations do depend on desalination technology for their survival. 8 countries could meet all their freshwater needs by evaporating seawater. Now, that's a simple process of evaporation. What you do is, think of a very simple experiment. Get a bunch of seawater, and you put a little dome over it, leave it out in the sun, right? And you see what? Condensate form on the globe, on the underside of it. You want to save that. That's drinkable. What's left behind is not. You leave it behind. So someone said, if you were stranded on a desert island, what would you want to take with you? And most people say, well, I want this CD of this musician or this rock band. I'm like, give me a frickin' goddamn plexiglass dome so I can have water. Now, from the desal plants, the waste tend to be directly discharged into the oceans, surface waters, or sewers, injected into deep wells, or left to, in basically evaporative ponds. Untreated, it was a threat to marine ecosystems. On land, it enhanced the increasing hazard of soil salination. Okay, let's first tackle the threat to marine ecosystems. If you get out into the open ocean, or the deep ocean, most organisms are what we call stenohaline. Haline refers to salt, like thermohaline circulations. Right, thermal temperature haline, temperature salt circulations. Stenohaline basically is the term that's used to describe organisms that can only tolerate a very narrow range in the salinity content. Contrast that with organisms that are found in estuaries, where you have a wide range of salinity over the course of 24 hours. Such organisms are called euryhaline. They can tolerate a exposure to a wide range of salinity. Their physiology can deal with it. And a stenohaline organism, their physiology is not set up to deal with a wide range of salinity. That's the threat. A euryhaline organism can probably handle a brine dump, if you will. A stenohaline? No. And that's the threat to the marine ecosystem, that it will compromise the physiology of the stenohaline organism, will not be able to handle the increased salinity. And they'll end up actually losing fluid from their tissues and dying. Whereas the euryhaline, the euryhaline organism can probably handle it, up to a point. Euryhaline organism can handle, salinities on average between 10 and 25. You start pushing to that 30, which is what we define open oceanic water salinity, they could still have a problem. So they may be able to tolerate it a bit better, but it all depends on how much brine is dumped in there. Will actually determine overall survival later on. Now, as far as the issue of soil salination, if you put too much salt in the roots of the plants absorb, it will kill the plants. That's the problem. Now, it is possible to use this brine. So you could possibly use it in aquaculture or nourish salt-tolerant crops. Salt-tolerant, that means they can handle salt. Now, what's some of the elements that we find, and think of them in the ionic states? Sodium, magnesium, calcium, potassium. Okay, so those first few are part of the metals, the alkaline earth metals. Bromine, okay, is a halogen. And we have strontium, lithium. Lithium is also a alkali metal. Rubidium, and even uranium. They could be exploited for industry and agriculture as well. But there aren't the technologies yet to extract such elements economically. So this needs to be developed if you're going to do that. If you want to avoid dumping all that in there. Now, of course, companies looking at the bottom line, they're just going to say, screw that, we just want to dump. Be rid of it. Well, if you have other industries that develop ways to utilize this, then those companies that make the brine, they can then sell it. Instead of dumping, they can sell it and let those companies do what they need to do with it. So Manzoor Kadir of UNUINWEH, who's one of the authors of the study, says there is a need to translate such research and convert an environmental problem into an economic opportunity. This is particularly important in countries producing large volumes of brine with relatively low efficiency, such as Saudi Arabia, UAE, Kuwait, and Qatar. Using saline drainage water offers potential commercial, social, and environmental gains. Reject brine has been used for aquaculture with increases in fish biomass of 300% achieved. It has also been successfully used to cultivate the dietary supplement spirulina and to irrigate forage shrubs and crops. Though it might be leading to a later problem, land salination. Salinization. Yeah, salinization. Yeah. Now, the only way you get politicians to act on anything is to basically wave dollar amounts in their faces. They're not going to really care about environment, not too many of them. But you put a price tag on things, yeah, they'll get their, oh, this will create jobs. Yeah, then they'll get and do something about it. So, having to argue the political and economic aspect is every bit as important as to just talking about the science. You can talk about the science and you're going to get what? Glazed eyes. I hate to say. But if you start taking that science and saying, okay, these are the ramifications of it, but here is an economic opportunity which would be politically savvy for a politician to embrace, then you might actually get things done. So, researchers at the International Institute for Applied Systems Analysis in Austria also think that a twofold approach to this world water crisis, and they report in the journal Environmental Research Letters that they want to see the provision of water and sanitation from any source and action on climate in an integrated approach. That's basically their position. These are both among the 17 Goals of Sustainable Development adopted by UN agencies in 93 nations. And the IIASA researchers think, that's International Institute of Applied System Analysis, for example, that water pumping and treatment plants could also work with nations' electricity grids to make the most efficient use of both. So, in the process of pulling salt and making potable drinking water, maybe you can perhaps create some energy. So Simon Parkinson, who's a researcher from IIASA and also associated with the University of Victoria, and he led the study, he states that the results of our analysis show that combining clean water and climate policies can increase implementation costs, but these increases are relatively small in comparison to the cost of implementing each policy on its own. So you combine things, you get a synergistic effect, help each other, end up in the long term being cheaper. So if I want to implement 3 policies, and the 3 policies might cost me, say, $3 billion, but I combine them, and the 3 policies combined, implemented all at once, cost $1.8 billion, that's $1.2 billion that you saved. That's kind of what the point he's making here. He concludes that finding and improving synergies between decarbonization and water efficiency is crucial for minimizing joint policy implementation costs and uncertainties. So you have the issue of creating too much brine, which can be detrimental to organisms, but there are ways, but it can have some possible uses. We have desal plants providing drinking water. There's the problem of the energy, there's the problem of the brine. What they're basically saying is, let's take these negative aspects of it and turn it into a positive. That's in essence what they're saying. So, thank you for your time. We'll talk soon. Hey folks, this is Jim here reminding you to subscribe to this channel, to share my videos, tell others of the work that I do here. I also ask that if you are not already a patron at Patreon, to please consider becoming a patron at Patreon. You can find the information in the description box below the video. I'm asking you to help support the work that I do. I do not take any money from corporations or from any other sources, so the information I share with you is the actual science as it comes out of the peer-reviewed journals. So there is no BS, there's no propaganda, there's no agenda. It's just I present the science and I explain to you what it means, or at least my interpretations of it, based on my own experience as a scientist. I want this channel to grow. I consider, while I discuss many different topics here, you've noticed I do focus a lot on climate issues. I consider climate change to be the most pressing issue facing humanity today. Thus, I consider it important to disseminate this information to a wider and wider, more and more people. And I need your help to do this. So, yes, please subscribe. Please tell others of the work that I do here. Please share my videos on social media platforms, with your social media groups, what have you. We need to get this information out there. So for those of you who are supporting me on Patreon, I thank you greatly for your support and continued support. It does mean a lot to me. So together we can get this information to more and more people. Thank you. Thank you for your support.